pressure drop for the heat exchangers is fairly nominal on how you design it. You can design for 100 kPa or you can design for 25 kPa. If you're running the heat exchanger at full capacity at 100 kPa and then halve the flow rate, you divide your pressure drop by 4, so 25 kPa. The problem comes in that if you design for 25 kPa for full flow and you halve the flow rate, now you've got 5 or 10 kPa pressure drop through the heat exchanger. Fouling is also related to wall shear. So fouling starts to increase with low velocities. So one has to look at how you design for winter and how you design for summer and come up with a compromise. Just saying one competitor has low pressure drop versus another competitor is not the right way of going. And don't forget, pressure drop is a sacrifice for heat transfer area. Low pressure drop designs cost you more to buy. So one has to look at the type of water, how you're achieving the heat transfer area, and in regards to how the heat exchange is going to foul up over time. In the norm, Alfa Laval will design the heat exchangers at around 100 kPa if we are not given any limits. That's just a normal thing we do, but it could easily be 125 kPa or 75 kPa. If a client says we want 10 kPa, we will design for 10 kPa and show them the difference between 10 and 20 kPa. There's a huge difference in the size of the heat exchanger. Overlapping that, when you start looking at the temperature profile, if the temperature profile is fairly close, like 1 degree, you want a very efficient heat exchanger. And you choose a certain plate geometry to give you that high heat transfer efficiency. But the low pressure drop kind of negates you using that because that's a high pressure drop plate. You need to use a low pressure drop plate. So again, it's all a case of sacrifice and compromise. That's something you've got to sit down with the contractor or customer and come up with an acceptable design. If there's limited space, you're better off with high pressure drop, because that means the heat exchanger gets smaller. And there could either be less heat transfer plates in the same frame, or you'd be able to change the channel gap, or even shrink the size of the heat exchanger. And this is what we've done in the past. Clients have come to us and said, oh, I got 10 kPa and I have limited space. No heat exchanger will fit in there because it's just not enough space. So we can get them to compromise on the design pressure drop, and we can shrink the heat exchanger down to fit. The only compromise, well, two compromises, apart from the size of the heat exchanger, is going to be the cost of the pump and the cost of running the pump. Flip that over then, if you're using a cooling tower as your cooling medium, the higher the pressure drop, the less maintenance you will spend on the heat exchanger itself. So you've got a higher pump energy then compared against your maintenance cost. And we can show how fouling starts. As your velocity through the heat exchanger decreases, the fluid that comes in here, instead of going right across the face of the plate, tends to go down just one side. So you have little or no flow down this side of the plate. You're not filling it up at low pressure drops. So fouling starts to take off on this side of the plate and then moves across. So eventually you block the channel when you've got such low pressure drops. And the tendency is that a lot of designers will quite easily acquiesce to the customer's requirements without talking or understanding the mechanism of how pressure drop works on the distribution of the fluid across the plate.